My name is Manish Kumar and my enrollment number is E19CS8102. I'm a third year BTech student of Computer Science of Bennett University, and today I will be doing a seminar on quantum computers. So let's begin.
For most of our history, human technology consisted of our brains, fire, and sharpsticks. While fire and sharpsticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and the control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of data processor in computers, basically a switch that can either block or open way for the information coming through. The information is made up of bits that can be set to either 0 or 1. Combination of several bits are used to represent more complex information. Transistors are combined to create logic gates which can still do very simple stuffs. For example, an AND gate sends an output of 1 if all of its input are 1 and output of 0 otherwise. Combination of logic gate finally forms meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all the basic operations are simpler than first grade math, you can imagine a computer as a group of 7-year-olds really answering simple basic mathematical questions. A large enough bunch of them could basically compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics is making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another. So a switch is passage that can block electrons from moving in one direction. Today, a typical scale for transistor is 14 nanometers, which is 8 times less than that of HIV virus diameter and 500 times smaller than that of red blood cell. As transistors are shrinking to the size of few atoms, electrons may just transfer themselves to other side of blocked passage by the process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable way we are used to. The traditional computers just stop making sense. We are approaching a real physical barrier to our technological process. To solve this problem, scientists are trying to use the unusual quantum properties to their advantage by building quantum computers. In normal computer, bits are the smallest unit of information. Quantum computer uses qubits, which can be set to one of the two values. A qubit can be any two-level quantum system such as spin and magnetic field, or a single photon. 0 or 1 are this system possible state, like photons horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of these states. It can be in any proportion of both states at once. This is called superposition. But as soon as you test its values, say by sending a photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it is unobserved, the qubit is in superposition of probabilities for 0 and 1, and you can predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power 4 different configurations at a time. That's 16 possible configurations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store a million values in parallel. A really weird and intuitive property qubits have is entanglement, a close connection that makes each of the qubits react to a change in other state instantaneously, no matter how far they are apart. This means when measuring just one entangled qubit, you can deduce the properties of its partner without having to look. Qubit manipulation is a mind bender as well. A normal logic gate gets a simple set of input and produces one definite output. A quantum gate manipulates an input of superposition, rotate probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them, and manipulate probabilities. and then finally measure the outcome, collapsing superposition to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculation that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results and it will be only probably be the one you want. So you may have to double check and try again. But cleverly exploiting superposition and entanglement, this can be exponentially more efficient than it would ever be possible on a normal computer. So while quantum computers will probably not replace our home computer in some areas, they are vastly superior. One of them is database searching. To find something in database, a normal computer may have to test every single of its entities. Quantum computer algorithms need only square root of that time, which for large database is huge difference. Most famous use of quantum computer is ruining IT security. Right now, your browsing, email, and banking data are being kept secure by an encryption system in which you give everyone a public key to encode message only you can decode. The problem is that this public key can be used to calculate your secret private key. Luckily, doing necessary maths on a normal computer would take years of trial and error, but a quantum computer with exponential speed could do it in a breeze. Grover's algorithm, also called the amplitude amplification trick, is a way of increasing the chances that we will observe a quantum system in a particular state that we are interested in. It consists of two parts, the first being an algorithm to select the states we are interested in amplifying. For Grover's algorithm to work, this part must take an state vector describing all possible results and then flip the phase of the specific results we are interested in. Right now, a multiplication comparison circuit doesn't quite work this way. To start, we need to rotate the phase of the states where the output is 42. This is done by simplifying, applying the Z gate to the qubit representing the output of the comparison circuit. Recall from earlier that this is not just being applied to a couple of values. This phase rotation is applied to all states where input multiply to make 42. These states where inputs multiply to make something else has their phases unaffected by Z gates, since the comparison circuit would output a 0. We now need to disentangle the qubits representing the inputs from the qubits representing the intermediate results of each logic gate. Remember that applying our quantum multiplication circuit at the start effectively permutated a state vector where all possible inputs have some probability to make a state vector where all possible inputs and their corresponding effects on classical logic gates are equal likely. If we apply this circuit in reverse, this permutation is undone. Because of this, if we apply our reverse circuit after Z, the gate we will end up with a state vector where the only likely state are the ones where all adjacent qubits are 0. Just like we started with, since our circuit is just a permutation, the phases of the state we are interested in are flipped. Now that we have a circuit that satisfies the first part of the Grover's algorithm, we can treat it like a black box in case called as an oracle. If we pass any state vector, it will flip the phases of the state we are interested in. In this case, those states are the ones that represent the number that we multiply to make 42. We can now move on to the second part of the Grover's algorithm. To make thinking about this step more intuitive, we will represent the state vector of the quantum system as a combination of two other state vectors. The first is the state vector where only likely outcomes are the ones we are interested in, without their phases being flipped. The second is state vector containing all the states we are interested in. Notice that our state vector is no longer concerned with the states of extra qubit needed by our multiplication and comparison circuit. That is because we designed them to assume that these qubits will initially always be 0, and we took special care to put them into this state when we were done. In other words, our oracle doesn't entangle extra qubit with qubits representing the factors, so we don't have to worry about them for this part of the algorithm. We can also refer to the state vector where all the states are equal likely S. S is then a combination that contains mostly S prime. A little bit of W. This can be represented using a graph where prime is x-axis and W is y-axis. When we apply our oracle to the state the vector, we flip the phases of all the outcomes that we are interested in. Notice that our flat graph is actually sufficient to represent this as the phases involved in Grover's algorithm will never be anything except exactly 0 radian or pi radians. The next step is then flip our state vector across S. In other words, if we express our state of vector in terms of S, we want to flip the face of all components perpendicular to S. The second step is called diffusion. The way this diffusion is transformed is by passing all the qubits through an atom gate. Recall from earlier that when this gate is applied to a single qubit system where all outcomes are equal likely, the result is that only 0 is likely. Applying the Atmer gate again undoes this conversation. Similarly, when the gate is applied to the multiple qubits, the result is that the amplitude corresponding to all 0 state represents how uniform the original state vector was. In other words, it represents a coordinate along the s-axis. All the other amplitude represent coordinates along perpendicular axis effectively, meaning that they can represent the specific way that original state vector differs from S flipping. These phases then flips the state vector across S. We will finish up by applying the atom gate to the all qubits a second time to undo the coordinate transformation we have required. If we step back and look how these step works out graphically, notice that how state vector ended up pointed towards W and less towards S prime. If we repeat in this process, we notice that this effect gets stronger every time, but all this ends up meaning is that if we are looking for interesting states out of n possible states, the number of times we need to repeat this process is square root of n over m. This is another illustration of power of quantum computing. With classical computing, searching through n items often take n computations, especially with the problem of factoring a number. There is little that can be done to avoid searching through a large number of problem combinations to try and find at least the multiplies of a number of interest. Finally, we have completed our algorithm by applying the steps of Brodler's algorithm 10 times. We will produce an integral system of qubits that we are likely to be observed as representing number that multiply to 42. Another really exciting new use is simulations. Simulations of quantum world are very intense on resources, and even for bigger structures such as molecules, they often lack accuracy. Quantum simulations could provide new insight into proteins that might revolutionize medicines. Right now, we don't know if quantum computers will be just a specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there is only one way to find out.